Good afternoon, everyone. My name is Vikram, Assistant Professor BMC. So I'm going to discuss the CPU scheduling concepts based on the operating system concepts. So we already discussed first come first served scheduling algorithm in the last class. We have taken a snapshot of three processes that arise at time zero, having burst time of 24 milliseconds, 3 milliseconds, and 3 milliseconds for process 3. So if you allocate the process in first come first served basis, you see that the waiting time for P1 is 0, P2 is 24, P3 is 27, and average waiting time comes around 17. So from the Gantt chart, we can observe that waiting time can be calculated. P1 doesn't wait at all, P2 has to wait for 24, P3 has to wait for 27 milliseconds. The average waiting time comes around 17 milliseconds. So if the process arrives at all the time 0, the scheduler intelligently allocates the process in some order, so that the waiting time can be reduced. If it allocates in P2, P3, P1 fashion, and we use Gantt chart here, you can see that waiting time for P1 is 6, waiting time for P2 is 0, P3 is 3. Because if we allocate P2 first, P3 next, and P1 at the last, the average waiting time comes to a significant effect, a slowdown from the previous column. So thereby increasing the efficiency of the CPU. So this is a much better version than the previous one. So the thing is, whenever we use FCFA scheduling, if all the processes arise at time 0, scheduler can use intelligently and it can allocate short process behind long process. So that will increase the degree of multiprogramming. So next is shortest job for scheduling algorithm. Here we associate with each process the length of its next CPU burst. Using this length to schedule the process with the shortest time, it is optimal. It gives minimum average waiting time for a given set of processes. The difficulty is knowing the length of the next CPU burst. So here we will take a snapshot. We assume that all the processes are at time 0 and with the burst time of 6, 8, 7, 3. And we want to allocate all this process using Gantt chart technique. So here, which process is selected first based on the burst time. So whichever process is having shortest CPU burst time, that process is taken into consideration and that is allotted to the first slot. So P4 is having shortest CPU burst time of 3 milliseconds, that has been allotted first. Next process is taken as P1 because the burst time of P1 is 6, which is less than 8 and 7, so P1 is allotted. Next P3 is allotted for a period of 7 milliseconds, then P2 is allotted for a period of 8 milliseconds. So average waiting times comes around 7. So the main challenge here is to determine the length of the next CPU burst. So how can we determine the length of next CPU burst? We can use an exponential averaging formula which says that tau of n plus 1 equal to alpha into tau Tn plus 1 minus alpha into tau n. The Tn gives you actual length of nth CPU burst. Tau of n plus 1 gives you predicted value of the next CPU burst, right? Tau n gives you the previous CPU burst. Normally alpha is set to half because alpha varies from 0 to 1. You can take any value between this range. So alpha is set to half. Now you can see from this graph how we can predict the length of next CPU burst. So this gives the previous CPU burst, the blue line. The current CPU burst is given by the black line. Right. So based on these two values, we can determine the next CPU burst time. So we have 10, the previous CPU burst. Current CPU burst is 6. Based on the above formula, tau of n plus 1. What is tau of n plus 1? Tau 1 equal to alpha into Tn. Tn is the current, that is 6, plus 1 minus alpha into tau n. Tau n is 10. So here alpha half into 6 plus half into 10. Half into 6 plus half into 10, that is 3 plus 5, it is 8. Similarly, if we have the current CPU burst as 4, then previous CPU burst as 8, half into 8 plus half into 4, that is 4 plus 2, 6. Similarly, 6 is the next CPU, current CPU burst, 6 is the previous CPU burst, half into 6, that is 6. Similarly, we can find all the values by using the exponential average formula, where alpha is set to half. So however, if alpha is equal to 0, tau of n plus 1 equal to Tn, tau n, recent history, that means the current CPU burst doesn't have any effect. If alpha equal to 1, tau of n plus 1 equal to alpha into Tn. That means recent history has some effect over the last actual CPU burst count is going to take consideration. So next we'll take example of shortest remaining time first algorithm. So this is a preemptive algorithm. That means preemptive means the process can be preempted during the middle of its execution. So what we can do is we can take a snapshot of this. P1 arrival time we are going to take consideration. Burst time we are going to take consideration. The first process that is allotted to CPU is P1 because it arrives at time 0. Then at the end of first millisecond, P2 arrives, which burst time is 4 milliseconds. Now whether P1 should be preempted? No. Yes, P1 has to be preempted. The reason is P2, which arrives at time 1, is having burst time of 4 milliseconds. This is less than P1, which is having 7 millisecond shortest remaining time. Already 1 millisecond has been elapsed. Remaining time for P1 is 7 milliseconds, which is greater than P2. So P2 is shorter than P1. So P1 is preempted and P2 is being halted for a period of 4 milliseconds. Why 4 milliseconds? Now P3 comes at 2. When P3 comes at 2, it's going to compare, scheduler is going to compare the burst time of currently executing process and the arrival process. So P3 is 9, whereas P2 already it has taken 1 millisecond. Remaining time is 3 milliseconds. So 9 is greater than 3. So P3 is not, P2 is not preempted. At the end of 3rd millisecond, P4 arrives. P4 burst time is 5. Now at the end of 3rd millisecond, P2 would have been completed 2 milliseconds of its burst time. So 4 minus 2 is 2. So at the end of 3rd millisecond, P4 arrives. 5 is greater than 2. So P4 is not being allotted. So P2 is retained. So it is not preempted. So P2 is being allotted from 1 to 5. So once P2 is being done for completion, P2 is preempted. Next P4 is allotted instead of P3. The reason is P4 burst time is less than P3. So P4 is being allotted on gentle completion. Then P1 is not being allotted compared to P3 because 8 is less than 9. So P1 already it has taken 1 millisecond here. So remaining time is 7. So 7 is less than 9, 7. And P3 lasts 17 to 26. So thereby the average waiting time comes around 6.5 milliseconds. So this is how preemptive shortest job first scheduling algorithm scheduling is going to work. Shortest remaining time first algorithm. This is one version of preemptive algorithm. So next we have priority scheduling. The priority is associated with each process. The CPU is allocated to the process with highest priority. The smallest integer equal to highest priority. It can be preemptive or non-preemptive. So STF's priority scheduling, the priority is the inverse of predicting CPU burst time. Starvation, low priority process will never execute. This is one of the problem of priority scheduling is starvation. Because if the process is having lowest priority, then it may not get a chance to be allocated to the CPU. So one solution is we have to increase the priority of the process as the time progresses. So this is called as aging. Aging technique we are going to follow so that the priority of the process is going to be increased. Now let us say, take a snapshot, we'll see how the priority scheduling is going to work. So lower priority is having here, smallest integer is having higher priority. So if there is having smallest integer, the highest priority is taken and then it is allotted according to the Gantt chart, and average waiting times comes from 8.2 milliseconds. So next we have round robin scheduling algorithm. This is also called as preemptive scheduling algorithm. This comes under preemptive scheduling algorithm. It works in FCFS order, but with one constraint is each process is given a time quantum. Within the time quantum, the process has to complete its task. However, if the process doesn't complete its task within the time quantum, it is preempted, and then later it is allotted at some point of time. Now let us see an example. We have P1, P2, P3. P1 is having 24 milliseconds, P2 is having 3 milliseconds, P3 is having 3 milliseconds. Now P1 time quantum is given as 4 milliseconds. First P1 is allotted according to FCFS scheduling algorithm. 0 to 4 milliseconds has been allotted. Now its time quantum is over. Within the time quantum, P1 has to complete its task, but it takes 24 milliseconds to complete. So if a round robin will preempt this process P1 and allocate the next process in the queue. P2 is 3. So P2 is been allotted. So P2 has to complete within the 4 millisecond of time quantum. So P2 has only 3 burst time. So P2 will complete. And P3 also complete because 3 milliseconds. And later P1 is being allotted again repeatedly. So that way, that is how round robin scheduling is going to work. So typically higher average turnaround time than SJF, but better response. Queue should be large compared to context switch time. Queue usually 10 milliseconds to 100 milliseconds. Context switch is less than 10 milliseconds. So if the time quantum is high, then the context switch is very less. It's almost negligible. Because if you give a lot of time quantum, most of the process will complete within this time quantum. If the time quantum is set, if the time quantum is very low, you can see the number of context switches it takes is more. If time quantum is medium, then context switch is again very low, but it will have some effect. So here, as the time quantum is very less, the number of context switches it takes between each process is more. So this is how round robin scheduling is going to work. There are some other algorithms like multi-level, multi-feedback queue scheduling algorithms, real-time scheduling algorithms, which are discussed in the CPU scheduling concept.